Hello, everyone, and welcome. Thank you for coming today, and for those joining us online, thank you for watching. So we're here to talk to you a little bit about 3D printed joints and connectors for multiple assemblies. So, as Michelle said, my name is Jacob Floyd, and I'm a senior in computer engineering.
And my name is Nick Russell. I'm a junior here in mechanical engineering. So what we're going to talk to you about today is we'll give you an overview of REU program, which stands for Research Experience for Undergraduates, which is what we did this summer and how we got involved in this program. We'll talk a little bit about additive manufacturing and fused deposition modeling technologies. We'll tell you about the InnoDino project that we worked on this summer, tell you more about what we accomplished, and then a conclusion. So what is an REU? It stands for Research Experience for Undergraduates. It's a program that supports research internships for undergraduates at centers funded by the National Science Foundation across the country. And it gives students a way to get meaningfully involved in undergraduate research that supports other NSF-funded research at different universities around the country.
So the way that these REUs can happen is that faculty, staff, or maybe departments will write a proposal, and they will give this proposal to the National Science Foundation, and they will review it and decide if they will do an REU site at this location. So Tennessee Tech was very fortunate. We have 2 REU sites this past summer and in the future too. And as you can see, our REU that we were actually involved in was the Manufacturing and Techno-Entrepreneurship REU. There was also another one in the ECU department that was the Secure and Privacy Preserving Cyber Physical Systems REU.
So to be eligible to apply for a REU, you have to be a U.S. citizen or permanent resident in engineering, computer science, or other engineering technology area, 3.25 or higher. You have to be an undergraduate and must be graduating after September 2016. So those are just the requirements. A lot of the REUs are competitive, and you can apply nationally again. And the award is $5,000 for 10 weeks, and that's like your stipend or payment for the internship. You can either live on campus for free, or if you live off campus, there's an additional housing stipend, a food allowance, and then travel if you're driving or need airfare accommodations. The program that we did here at Tech, like Jacob mentioned, was the Advanced Manufacturing and Techno-Entrepreneurship. So this one was unique across the country in that it had the entrepreneurship aspect, and we did that by incorporating Lean Launchpad, which is another NSF initiative. So that was an additional class we took this summer, where we looked at commercializing different aspects of our research project. We also visited Oak Ridge to ORNL and Nashville to Launch Tennessee and other facilities in both of those cities. And then we did other training outside of our research, which included how to use a library, graduate school, research, safety training, how to take the placement examinations for graduate school, solid modeling, and also some web design.
So this picture that you see here is a graphical representation of some of the hiring trends in additive manufacturing over the past few years. As you can see, it has been on the rise. So we foresee that additive manufacturing is going to be really booming in the future, and there's definitely job growth, and hopefully many people will acquire jobs in this industry in the future. So what is additive manufacturing? Well, in the past, the traditional types of manufacturing were called subtractive manufacturing, such as your typical CNC, milling, plating, where you take an actual object and you have to cut it down to the product that you want. Additive manufacturing is when you start with the raw material and you build it up layer by layer. And you can trace different types of additive manufacturing back to the 1980s, such as the SLA powder additive manufacturing, but just recently it's really started to boom due to the development of FDM Technologies.
Yeah, so under this additive manufacturing framework, you kind of have different technology sets that have been developed and then different materials that can be used by the technology sets. So on the right in technologies, you have selective laser sintering, which is where you usually will lay down a powder bed, hit it with high energy laser, and it'll melt the powder into the shape of whatever you're trying to make, and then it'll build up layer on later. FDM, or fused deposition modeling, you actually have an extruder that kind of works like a hot glue gun. It'll move on a multi-axis machine and build the product up like that. And then stereolithography, which is the longest word I think I know how to spell, is basically you have some kind of photopolymer or something that reacts to light or different stimulus, and then you would actually like pull it out of a bed of resin that you're exposing to different frequencies of light. And so for the materials, you can do, polymers and plastics is most common because it's inexpensive. Metals show a lot of promise, but there's still a lot of work that has to be done on material properties and making machines less expensive. And there's some exotic things that you can print with, food, wood, bone, or even glass, which is pretty interesting. So here at Tennessee Tech, we're blessed to have a lot of great additive manufacturing facilities. So the makerspace, which we're in, if you look to your guys' rights, you'll see a lot of 3D printers, which you can use. You have the Digital Manufacturing Demonstration Lab, the Remotely Accessible Additive Manufacturing Lab. We'll be doing the AM Watch project out of the STEM Center, various engineering department labs, as well as the College of Education has one that teachers can be taught on. So Tech is a leader regionally and nationally in terms of having access to facilities where you can utilize 3D printers.
So the technology that we used the most this summer was FDM Technologies, which is fused deposition modeling. And basically, this is, in the type that we used, is where you have the raw material, which would be PLA or ABS plastic most of the time in our research. And this would be extruded through the 3D printer nozzle because it would be heated up, melted, and extruded onto the print bed, and then it would print your part one layer at a time. And so what you could do is you'd have your 3D model, which is typically an STL file, and this file would be broken down mathematically into the code that the machine can understand. And then the machine uses that code to print your part. So then you can just start it, it'll print your part, and then when it's done, you have an actual physical object that you can hold, and that functions in the way you hoped it for. So this is a chart of the 3D printers that we mainly used this past summer. We used the MakerBot Replicator Z18, which is in the makerspace, PrinterBot Simple Metal, which is over in Lewis Hall in the Rapid Prototyping Lab, and also the Ultimaker 2 Extended Plus. So just some differences between the printers. The most expensive one was the MakerBot. However, it was not our favorite printer, I guess you could say, just because of the slow print times and some of the quality prints. However, it did have the largest print beds. So for a lot of the parts that we were printing, they were just too big for our smaller printers. So we would bring them over here and print them. And sometimes we even had to print them in separate parts. And we'll talk about that a little bit later. But you also have to just look at the overall cost, such as the PrinterBot. It's only $600, which is a great deal for a 3D printer. And the quality was really amazing for a piece of equipment that was so low cost. And then the Ultimaker 2 was our main go-to 3D printer this past summer. It was very high quality, and it was also in between the expensive levels of the MakerBot and the PrinterBot. So, and it was just very dependable. We could just go in, start a print, leave, and it would come out looking great.
So now we'll talk more about what we actually did this summer. So what you see before us is a picture of our team. So Dr. Fadon was our principal investigator. He had Joe Caston, who has returned to Western Illinois. And the main thing we worked on is the Struthiomimus dinosaur, which is actually sitting behind you guys right now. So if you remember, a year and a half or 2 years ago, we had the real Struthiomimus dinosaur, and it was sitting in the window kind of gallery out there in front of the BizBox. And that Struthiomimus had to go home, but Tennessee Tech really liked it and wanted another one. So we began on a journey to reverse engineer the dinosaur we had and to create a new model of it. So we took that dinosaur skeleton and scanned the bones using some scanning equipment that we have here at Tennessee Tech, and it generated these 3D point meshes. Then we had to go in and repair the meshes because the scanners don't work perfectly, and you clean up the image of the bone that you're able to get, and you prepare the bones for 3D printing and choose the correct orientation and the correct supports so that the print comes out looking like you want it to, essentially. You then do hours and hours of printing, and finally we assembled the dinosaur, put it all together.
So this is just kind of an overview of some of the journals and articles that we looked at, because most of the people in our group, none of us really knew a lot about additive manufacturing when we came to this REU. So we did a lot of research ahead of time. Just so we had to start from the basics and then work our way up. And by the end of the summer, I think we were very comfortable with many different additive manufacturing technologies. It was a great experience, and these research articles were great help in getting us started. So these pictures here that you see is some of our early conceptions whenever we first started the REU. we really weren't sure what direction we were going to go because we were trying to design these joints that were 3D printed. At the same time, we were learning how to use the printers. So one of the main things that we focused on in this first one was a single print joint where we actually printed the joint. We wanted to print both parts together. So instead of printing two separate parts and putting them together, we wanted both parts to print as one and then be able to move it. We discovered that it took a lot of trial and error to get this to work. We eventually were able to get it to somewhat work, but we decided that implementing that into our actual project and doing mass production, it would just be too hard to get a consistent level of print.
Yeah, so for context, we in a museum, a dinosaur is usually just going to be on like some kind of metal rig, and the bones may not even be connected at all. And we wanted to try to connect the dinosaur anatomically at different positions, so that it's in the spine or the knees, the elbows, make it to where it could potentially be repositionable. And so we started looking at different joints that could accomplish this. The next kind of phase of design that we looked at was we were trying a lot of different geometries. So the joint at the top right, for instance, my right, your left, is actually kind of has indentions like a golf ball. There's pegs within the socket, and so we were trying to play with frictional properties or mechanical interference. This snap joint was robust and it worked a lot of the time, but didn't limit your degrees of freedom. And we tried a modified snap joint. The reason we were trying so many different types of joints, now you think a ball and socket's pretty easy, but whenever you're trying to 3D print it, there are a lot of limitations. It offers a lot of geometrical freedom in terms of the possibilities, but to get the prints to come out and work well, we actually had a lot of issues that we had to troubleshoot. So we were trying lots of different geometries to see what prints would come out successfully on the machines we used. In the final iteration, the two top images where we're using like mechanical friction, so we could print screws and nuts and actually tighten down and create mechanical friction so that you could position an arm or a leg and then tighten that screw down to keep it in place. And the modified ball and socket joint was the final ball joint design that we went with. And we used two different materials. We used nylon for the ball because there's stress concentrators at the top and bottom of the ball, so nylon was more flexible. And then for the socket, we used PLA because it didn't stretch as much, so it would maintain its shape over time if you actually move the ball and socket around a lot.
And just to add to that, go back one slide. The joint in the top right corner, we also use that a lot in the Dinosaur. We use this on the arms and the legs because you can the two pegs you see, that one actually goes into each leg, and then you can tighten it down with like a socket wrench, and it worked really well. You could position your bones the way you wanted it and tighten it down, and they would hold that position. So this spreadsheet that we have here is just kind of a demonstration of the overall material cost that we had, which was very, very low. It only cost us $246 in materials to make that Dinosaur, which is amazing compared to how much it would cost to make it in the standard way of manufacturing, which would be casting. So there's a huge benefit in the cost. The only bad part was the time. If you started today and printed nonstop, it would take you 47 days to print the Dinosaur, which is a long time and a lot of print time. But in the end, you have to weigh your benefits. And we thought that it was great that it only cost about $250 to 3D print the whole Dinosaur. So one of the problems that we had was some of the bones were so large that we couldn't print them in any of the printers that we have. So what we had to do was actually take the bone, which in this case was the pelvis, and we split it into 4 different sections. And all 4 sections were printed on the Z18 actually. And once those sections were printed, we actually put them all together by using epoxy and 3D printing pins. And we kind of did it like you would do like a TIG weld, but except you're using a 3D plastic pin. It's a really cool method. So that was one way that we were able to put all 4 pieces together and make one part out of 4 different ones.
So we were well on our way to designing and assembling the Dinosaur, having joints to connect it. But we kind of realized that the joints weren't going to be strong enough to hold the entire Dinosaur because it ended up being heavier than we expected because the fill density on certain parts had to be high. So we wanted a stand that would hold the dinosaur, and our main design goals were that it was minimalistic, visually appealing, innovative, that it was different than how dinosaurs are currently held up in museums, because we didn't want to do what other people do. So we began the design phase with some static analysis. So you know from biology that the dinosaur is symmetric about its midpoint, but we wanted to know, based upon this blueprint and the XY, where we should put supports and how the dinosaur would have like moments around the supports that it could be well supported, because it turned out to be really long. So moment arms are as important as the weight. So we did a static analysis where we subdivided the blueprint into a bunch of squares that represent the mass that would be there. And then just basically found its centroid, and it's at the red dot, which is here. So below the pelvis, a little bit in front of hips, which is what you'd expect from a biological standpoint. So that was good to find, and it helped us know where we should put anchors, how to support the dinosaur.
So this next picture is just kind of showing how we took that a step further. Nick actually took those blocks that he made in SolidWorks and moved them over to the stand. So this helped us get a visual idea of, okay, what is this dinosaur going to look like when we actually put it on the stand? This was a great help in letting us know if we wanted to pursue the stand design or what changes we needed to make, and we were pretty happy. So then it came to assembly. We actually bought this purple and gold lake sand, and then it was CNC'd at a local company, and we put it together, and it was a good long process, but in the end we came out with a great result. I think it greatly advertises the new logo for Tennessee Tech, and it turned out to be a really beautiful sand design.
So the last 2 weeks we were really in Dinosaur Assembly. So over the summer we printed out probably over 100 bones in different sections, which we had to glue together and weld. And we also had to use the different joints that we designed, insert them into bone sections, fuse the joints to the bone sections, and then actually mount it to our stand. And of course there were mistakes that were made, things got broken. So it's an iterative process to get it on the stand, but we were finally able to accomplish it. So in terms of some of the problems that we faced over the summer, is a lot of the parts that you'd want to print are too large for a bed, and there's not a lot written out there of how to fuse different parts that you print. So we had to come up with several different ways of rigging them together, whether it be with the 3D printed pins or with JV welds. And there's not a lot of understanding of the physical properties of those, like whenever you fuse these 3D printed parts together, so that would be good research. Joint strength and durability. So the bulk properties of these plastic materials that you get from a manufacturer, but whenever you print them, you don't know how a joint or some type of whatever product you make, you don't know how it's going to perform. So we can definitely do a lot more work in understanding, if you have a printed design, how is it going to behave under stresses or loadings. The 3D printers on campus, we talked about some of the different types, and they produce different quality of prints, and sometimes they don't have the same properties and aren't necessarily interchangeable, so it'd be good to understand that better. The Dinosaur Assembly and final touches, like I said, it fell apart a few times. The dinosaur ended up being bigger and heavier than what we were advised it would be. And lastly, we're not paleontologists or geologists, so whenever we're trying to build a dinosaur, there wasn't a ton of material out there about how Struthiomimus bones go together, and we had to reconstruct it. So we learned a lot about dinosaur anatomy, interestingly enough, which was really neat.
So some future work that we could possibly do with this is it'd be awesome if we could go back and just redo some of the designs. There's different 3D models that maybe instead of printing two bones separately, we could model the bones together and print them together to make it overall more simple design. And then we've also thought about actually printing our joints into the bones. So instead of having a joint and having your bones, actually have a joint printed on one bone and a joint printed on the other bone, so you can just put them together. And then we would also just like to explore other mass production possibilities, and we've even talked about maybe scaling down the dinosaur and seeing how well it would print on different machine envelopes. So that way we could use maybe one printer for all the prints. So that's one option too. So in conclusion, the REU was a success, and we also discovered that additive manufacturing is a really innovative and growing field, and we think there's huge potential for it in the industry. We were also able to successfully reverse engineer the Struthiomimus dinosaur and 3D print it, and we feel like we had great success in our research, and we think this REU program will benefit us for the rest of our lives in education and industry.
So finally, we'd like to acknowledge the National Science Foundation for the award number 1461179, which is the REU Summer Research Internship in Manufacturing and Techno-Entrepreneurship, the Tennessee Tech College of Engineering and Makerspace, Dr. Ismail Fadan, who is our faculty investigator, Dr. Trevor Ensis, Dean of College of Engineering, Dr. Vahid Makvali, Associate Dean for Research and Innovation, and Michelle Davis, who is the coordinator at the Center for Manufacturing Research. So thanks everybody for coming. If you guys have some questions, and I'm going to throw my email. Jacob will put his on this final slide if any of you guys want to talk to us about anything else related to additive manufacturing.